Hello everybody. This is the video summary of the first talk at Math Society. So we talked about the Collatz Conjecture, and we talked about the arguments for and against it. So what is the Collatz Conjecture? Well, it's a problem that was formed in, I think, 1937 is what Wikipedia says. And it's infamous because it's so simple to grasp what the problem is, but it's so difficult to prove, and nobody has proven it so far. In today we talked about the arguments for and against it. So let's talk about what it is first. So you take a number n, integer. If it's odd, you times it by 3 and add 1, and if it's even, you divide it by 2. For example, if we take the number 5, we go 5, that's odd, so we times it by 3 and add 1. That's even, so we divide it by 2. 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 And we end up with 1. The Collatz conjecture says, every integer n will eventually end up at 1. So firstly, we'll talk about why this could be true. Okay, good. So, arguments for. Firstly, they've computed it for 2 to the power of 68 numbers. So, I mean, that's a lot of numbers, and it still has not broken or shown any signs of breaking at all. So, okay, that's the first piece of pretty convincing argument. Secondly, in 2003, it was proven that in the set of integers between 1 and x, so if we have 1, 2, 3, blah, 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 up until x, at least, okay, zooming in was not a great idea, okay, okay, let me write it up here then. So, firstly, there's the 2 to the 68 argument. Secondly, between 1 and x, so between 1 and x, at least x to the power of 0.84 integers will satisfy it. So that's a very close to just all of them, but not quite. So that's the second piece of evidence for. Is there a way to clear this? That's the question. Okay. Doesn't seem so, so I'll rub this bit out here. So those are the first two pieces of evidence, but there's more. Secondly, one counter argument could be that that the conjecture is false because there is a loop somewhere. If you look at a big enough number, there's a loop. Well, okay, that could be true, granted, but the loop would have to be at least 17 million digits long. Not digits, numbers. Numbers long. So I mean that is a massive loop. Like that would have to be a crazy counterexample for there to be a loop. The fourth argument is that 3x plus 1 seems to be very special. For example, if you try 3x plus 5, so for every odd number you do 3x plus 5, well now what happens to the number 5? Number 5 goes 5. Now because we're doing 3x plus 5 we go to 20. This is odd divided by 2. This is odd divided by 2. And all of a sudden you see that we have a loop. So already it's breaking down for 3x plus 5. And the same thing happens with 3x plus 1, 3x plus 3. So the 3x plus 1 seems to be especially kind of special because, you know, it would take quite something for there to be a... Because you get it instantly with 3x plus 5, but for 3x plus 1, we have to go at least beyond 2 to the power of 68 numbers to find a counterexample. And fifth, there's the 3/4 argument, which basically says that on average, an odd integer will be multiplied by a factor of 3 over 4. So an odd integer initially goes to 3n plus 1, but because n is odd, this will always be even, and so really it goes to 3n plus 1 over 2. Now there's a 50% chance this is even, so there's a 25% chance that n will actually end up going to 3n plus 1 over 4. 50%, so there's a 50% chance of this being even, and so there's a 12.5% chance that it would go to 3n plus 1 over 8, and so on and so on. So, if we take the geometric mean, I think it is, of all the ratios of these probabilities, we end up with, on average, an odd integer should be multiplied by a factor of 3 over 2 to the power of a half, because there's a 50% chance of it being 3 over 2, times 3 over 4 to the power of a quarter, times 3 over 8 to the power of an eighth, times blah blah blah, up until infinity. And this is equal to, well, on the top, we have 3 to the power of a half plus a quarter plus an eighth plus blah blah blah, which is just 3. And on the bottom, you should get 4. Should get 2 to the power of 2. If you rewrite all of these denominators as 2 to the power of n, and then you do the sum, you should sum of the powers, you should hopefully get 2 to the power of 2. So what does this mean? This means that so for every even number it's divided by 2, and for every odd number on average it's multiplied by 3 over 4. So this of course is less than 1, which means that on average, if we pick an odd number, it will decrease. And so this is a great counter argument to the argument that there could be some number that will diverge. Obviously it's not a proof against it, but it's a good bit of evidence against it. So those are the 5 main arguments, and if you're particularly interested in the Collatz conjecture, there's even more evidence which was discovered by a mathematician called Terence Tao in 2019. He basically said, well, I've come as close to proving it without actually proving it. And so, yeah, if you want to look that up in your own time, then I would definitely suggest it. And if you haven't heard of him already, definitely look up the mathematician Terence Tao, because he is one of the best, if not the best, mathematicians alive today. Okay, so this is a bit tedious. I'll hopefully have a better format for this talk video next time, but okay, I'm doing my best. Okay, so those are the arguments for. Now we look at the arguments against. Oh, I'm writing in white, that's why. Okay, against. Okay, what are the arguments against? Well, firstly, it hasn't been proven. Maybe the reason it hasn't been proven is that it's false. I mean, you can't prove something that is false to be true. So maybe people are trying to prove it true so badly, they're trying to do all of this and that, but the fact of the matter is it's just false. That's why you're not able to prove it. Second, 2 to the 68 is actually nothing, so it's quite funny that it's written in small digits. For example, there are some conjectures take up to 2 to the 1000, for example, to be disproven. So computational evidence is not strong. And the third argument is, well, even though it would have to be really long, there could be a loop. Slash divergent integer. Not integer, number. So, for example, the 3/4 argument is a good counter argument to the divergent part of this argument. So, for example, I could say, oh, well, there could just be an odd number that diverges. And then you could say, well, the 3/4 argument says that on average, even odd numbers decrease. So it's very unlikely that there will be one that diverges. However, I could then say, well, your 3/4 argument doesn't counter my argument that there could be a loop. So there could just be a loop that is like ridiculously long, but it turns out to be a loop. And yeah, that's basically a summary of what we talked about in the society. And I don't have much more to say. Hopefully, people who would just watch Gregorius Maths will have some like insightful comments as well. But yeah, thank you guys for watching.